going to learn about left and right Riemann sums. So Mr. Riemann, back long before there were calculators and you could do lots of stuff on all that using fancy technology. Before calculus, as we know it today, even existed, the idea that we were thinking about yesterday about the area underneath the curve started to be something that mathematicians wanted to know about. So Mr. Riemann had a method for estimating those things. So this first example we're going to look at says to estimate the area bounded by the x and y axes and the curve y equals 4 minus x squared. Okay, so the first thing I just want us to do is graph 4 minus x squared. And we're estimating the area bounded by the x and y axes and the curve. So x and y and the curve. I probably really should have just said first quadrant on this because I guess x and y and the curve is also over here. But we're looking in that first quadrant for this one. So if we graph 4 minus x squared, then that is just a parabola that's moved up 4 and flipped upside down. So if we graphed it 1, 2, 3, 4, 1, 2 over here, so we would have the point 0, 4, we would have the point 1, 3, and then we would have the point 0, 2. No, 2, 0. So we would have this graph right here. It did go back down over here, but we really only care about this area. So, what Riemann decided to do was he started off using rectangles underneath the curve. So you might, as we do this, you might think, wait, I think what we were doing yesterday was better than this idea, and it is, but when we get to the second part of these notes, you'll see why it is best to use easier to use the rectangles in some cases. So if I want to use rectangles under the curve, I have a couple options here. For this one, I'm going to split it up into 4 sections. I could use more rectangles, I could use less, but I'm going to just use 4. So if I want to use rectangles under the curve, if I split this right here into 4 sections, and so on the x-axis it'd be like 0.5, 1, 1.5, and then 2. And I'm going to make rectangles here. So I'm going to make my rectangles look like this. And then, do I even really have a rectangle for that last one? I don't. So it actually ends up only being 3 rectangles, although I'm using 4 sections here. So I have these rectangles, and I would want to find the area of each one of those rectangles. So area is just base times height. And so for each one of these rectangles, the base would be 0.5, right? So is it okay with you guys if I just sort of factor out my 0.5 there? So I'm going to have 0.5 times all of my heights. So the height of this rectangle is somewhere between 3 and 4. How do I figure out exactly what that height is? Good. So this is the curve 4 minus x squared. If I want to know any point on that curve, I just plug in the x value, right? So if I plug in the x value for 0.5, so I'm finding, I'm going to call this f, even though I didn't call it f of x here, f of 0.5, then I would have 4 minus 0.5 squared. 0.5 squared is 0.25, so I'd have 4 minus 0.25, which would give me 3.75. Right, so if I just plug that in, that gives me the y coordinate on the curve, which is the height right here. So I'd have 3.75 is the height of the first rectangle. Then I would need to find the height of the second rectangle. And so I can tell this one is exactly at 3. If I wasn't sure, I could plug in 1, 4 minus 1 squared That one's exactly 3. So I have 3 for the height of the next rectangle. And then for the third rectangle, I've got to find f of 1.5, which is going to be 4 minus 1.5 squared, and 1.5 squared is going to be 2.25, I think. So I will get 1.75 for that one. And then I'm going to do this for the very last one. Width would be 0.5. The very last one, the height is 0 for that one. Obviously, you don't have to include that because the height is 0. But if we had a rectangle here, it'd be right here, but it has a height of 0. That doesn't always happen depending on what section of the graph you're looking at. But for this one, it did. So if I type all of that in, 0.5 times 3.75 plus 3 plus 1.75, I'm going to get 4.25. Now this is an approximation. It is not the exact area. Is it an overestimate or an underestimate? If we're talking about like the actual area would be this whole area underneath the curve. We have just found the area of our rectangles. So it's an underestimate, right? So this one will be an underestimate in this case. So, but that does tell us for sure that the actual area is less than or is greater than 4.25. And we're pretending that we're Mr. Riemann and we are in the dark ages and we don't have a calculator, so this might be the best we can do, right? Even though I did use the calculator to add that last stuff up just because it was quicker. But they would have done all this, of course, without a calculator. Plus, they didn't have fully developed ideas of calculus at the time. I always think that's kind of crazy that like people were just sitting around thinking of these things and figuring them out. I do well with math. I understand it well, but everything I know, pretty much somebody's taught me. I mean, I figure some stuff out on my own, like different ways of doing things, but I'm not creating math nobody's ever thought about before. But to create math nobody's ever thought about before, that's pretty crazy. So that's what Mr. Riemann was doing whenever he was coming up with this method. Let's graph this again on the next one because we're gonna use a different method this time, a little bit different method. So same graph, same points. Okay, I am still going to. You know what? I messed up. Use rectangles under the curve. This one really shouldn't say under right there. Okay, so we used rectangles that were under the curve there. But that gave us an underestimate. So it might be helpful if we had an overestimate, and then we would know at least the actual areas between these two values, right? So to get an overestimate, we could do this. We're still going to split it into 4 parts. But instead of using that rectangle that was underneath the graph, I'm going to use this left point right here. I'm going to make myself a rectangle that goes just a little above the graph. And then I'm going to make me another rectangle that goes a little bit above the graph. And then another one that goes above the graph. And the last one that goes above the graph. So it's the same idea, but we're using that endpoint on the left hand side versus the endpoint on the right hand side. So if all of these still, this is 0.51, 1.52 here, so we still have a width of the rectangle of 0.5. And the height of that first rectangle would be 4. The height of the next one, that is going to be 3.75. That's the same value we had for our first rectangle on the other one because the height is the y-coordinate of this point right here. So it would be 3.75. And then the height of this one would be 3. Oh, no parentheses. height of the last one is 1.75. So if we add all that up, we get 6.25. And so this one is an overestimate. You can see because it's got this little extra part outside of the actual curve right there. So we would know for this that 4.25 is less than the actual area, which is less than 6.25. So somewhere between 4.25 and 6.25 we would have the actual area. All right. It's probably not going to be exactly halfway between. Depending on the shape of the graph, sometimes it would be exactly halfway between, but it's probably not in this case. So we wouldn't want to say just average those together and get an answer. Although if you did average them together and use that as your estimate, it'd probably be kind of close, right? It's probably better than 4.25 or 6.25. So this is a very sort of ancient way of figuring out that area underneath the curve. So let's think of some ways that we could make that estimate better. Okay, so any ideas, the estimates that we were just doing, what are some things we could do where we could still use geometry to figure out that area underneath the curve, but it would be better than what we just did? We could get something closer to the actual area than 4.25. We could do the trapezoids like we did yesterday. So the trapezoids have a lot less of a little gap there, so your underestimate's going to be a little bit closer for that. So trapezoids would work better. What if we stuck with the rectangles? What can we do still using rectangles that would make this better? They wouldn't really be triangles because, like, if you connected them right here, like that, that would be a trapezoid right there because you'd still have to do, like, the rectangle with the triangle on top. So if we just stuck with the rectangles, we're still doing rectangles, what else could we do that might make it better? What? Not really slope. We would, because if we're talking about slope, we'd be talking about like the derivative, and we really want the area underneath this. So, not necessarily the slope. What if I did this? What if I had that same shape, and I did this? Same exact shape, but more rectangles. Would that be better? Be a little bit closer, right? So if I'd used 8 rectangles instead of 4 rectangles, then it would have been closer. Or if I'd used 10 or 15 or 100, it would be a lot closer, right? So more rectangles. Would be a good option. And then the last thing that you could do, and I probably wouldn't think of this nearly as much, you could still use the same amount of rectangles, but rather than having the rectangles either using the left endpoint or the right endpoint on the graph, you could kind of do like a midpoint on the graph where the rectangles, they overlap kind of like this. Not the best picture in the world, but instead of using the endpoints, we kind of use that midpoint right there. And so a little bit of the graph there would be an underestimate, but then we'd have this overestimate on the other side, and those would balance out some. So we could use midpoint. Instead of the left or right. There. Those would all make these estimates better. In fact, midpoint and trapezoids, it just depends on the shape which one's going to be better. So for some, midpoint might actually be better than the trapezoids. For others, trapezoids might be better. But those are both going to be closer than just using left or right endpoints for those. So we are going to do trapezoids and midpoints some, but today we still want to mostly just focus on those rectangles. Okay, so I guess I should go back. This first one that we did, this is called a right endpoint Riemann sum. And it is called the right endpoint Riemann sum because the right top corner of the rectangle is on the graph. And the second one that we did, that was the left endpoint Riemann sum. So the left endpoint Riemann sum, the left top corner of the rectangle is on the graph. So we will see problems that look like this that you'll be doing for your assignment tonight. Estimate the area between the curve and the x-axis on the interval 0 to 3 using 6 sub-intervals. Now, for the sake of time, I'm going to go to Desmos and graph this because it's going to give us a beautiful graph that we can very quickly look at. So, what was that equation again? Y equals x minus 1 to the third plus 2. Alright, and the other good thing about Desmos, x equals 0, it's 0 to 3, right? X equals 0, x equals 3. So it'll put in these vertical lines for us. Let me scroll down a little bit here. So we're looking at this area right here. So you can see what we've got here. I'm just going to export this. And put this over here. Hopefully. It's going to be gigantic. Come on. And you do not have to graph these for this one. Okay? So, something a little interesting about this right here. Our right endpoint Riemann sum. So, if I take this, let me change this where it's thin. So, if I take this, and it told me I've got to use 6 sub-intervals. So, if I'm using 6 sub-intervals from 0 to 3, that means I'm going to have to split each one of these right here in half. So I'm going to have, I wish it was a little bit bigger, but this wouldn't fit. I wish it was right a little smaller. So, so when I do a right endpoint Riemann sum, it's going to look like, oh, I'm doing it wrong. Hold on. It would be like this. Something about like this. Okay, so something kind of interesting about this. No. What have I just done? Is that a right endpoint Riemann sum? It's not, because that is your left hand point right there. This is a left endpoint Riemann sum, which we also have to do. So let's just do that one first. So left endpoint, something kind of interesting about this, on this graph, is left an underestimate or an overestimate? It is an underestimate. If we go back, left was a specifically about when that happens later. But it depends on the graph whether or not it's going to be an overestimate or underestimate. Left or right is not always an over or underestimate for each one. So if we're doing the left endpoint Riemann sum, let's just think about this for a second. We are going to have each one of these little rectangles has a width of 0.5. Okay? And so I'm just going to think about this for a second, and if this was, let's say this was a function f here, then for the height of that first rectangle, I would need f of 0, right? That would be the height of my first rectangle, because that point right there would be f of 0. And then the height of the second rectangle would be f of 0.5. And then the height of the third rectangle would be f of 1. And the height of the fourth rectangle would be f of 1.5. And then the height of the fifth rectangle would be f of 2. And the height of the last rectangle would be f of 2.5. Okay, so notice I use 0, 0.51, 1.52, 2.5. I do not use 3, right? Because if I'm using six subintervals, I should have 1, 2, 3, 4, 5, 6 heights here. So use the first number. You do not use the 3 at the last. Because we are a little bit short on time here, and because I don't really want to do all of those, we'll call this f of x on Desmos. So f of 0 plus f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. So it plugs it all in for you right there. On your homework, I don't mind if you do this also here. Do please write down something for me. Don't just put the number that you get. So either write this down, or you could go ahead and plug it in and write those numbers down. But write this down if you want to use Desmos, or you could use your calculator. You could do the same thing in your calculator. Not that one, because that's the other one. But you could do the same thing in calculator. Do y1 of 0 plus y1 of 0.5 plus y, if you have that stored in y1. So you could do that same thing there. And so what did we just get? I didn't look at it good. 15.375. So we would have 0.5 times 15.375. And that is going to give us 0.5 times 15.375 is going to give us 6.1875. And that would be our underestimate for the graph. Okay. Questions on that part? Alright, so I'm going to now look at the overestimate for the graph. I'm going to color some more here. So if I'm doing right endpoint, that would be like this rectangle, this rectangle, this rectangle, this rectangle, about here maybe, so this rectangle, and then the last one would be way up here. So you can see that one would be a pretty big overestimate for this one. So if we were going to find the area, the area of all those rectangles, the width of each one is still 0.5, and the height this time, so for that first rectangle, if we're using the right sum, the height of that rectangle is not f of 0. It would be f of what? 0.5. And so the height of the first one is f of 0.5. The second one would be 1. The third would be 1.5. The fourth would be 2. The fifth would be 2.5. And the last would be f of 3. And because we don't have all that much time, and it is incredibly boring just to plug all those numbers in and find them by hand, and you got decimals, and it's just painful. So let's just go over here to Desmos. I'm gonna take out that f of 0. We'll come back. All right, take that out, that f of 0, and I'm gonna add a f of 3 here at the end, and I get 24.375. So I've got 0.5 times 24.375, and that is going to give me 12.1875. Okay, questions? Okay. So this is the general idea. Now, if I wanted to get a better estimate here, I could use more rectangles. So I'm not going to make you do more. But if, let's say we use 12 rectangles instead of 6 rectangles for this one. So from 0 to 3, if I use 12 rectangles, what would the width of each rectangle be? It's going to be 0.25, right? Because my total distance from 0 to 3 would be 3, and I'm dividing that by 12, and 3 divided by 12 would be 0.25. So I would have 0.25 times, and then if I'm going to do a left endpoint, then I would have f of 0 plus f of 0.25 plus f of 0.5 plus f of 0.75 plus f of 1 plus f of 1.25 plus f of 1.5 plus f of 1.75 plus f of 2 plus f of 2.25 plus f of 2.5 plus f of 2.75, and now it would stop, right? If I'm doing the left, we would start using 0, so we would not use 3, and so I'd get 8.67187. So that would be my underestimate here, which is pretty much higher than this one, right? And probably a lot better. And then if I wanted to make that an overestimate, I could just add f of 3 and take away that f of 0 on the beginning, and I'd get 10.92. So you're narrowing that in. And so at the beginning, whenever Riemann was doing his sums, they would do these Riemann sums with really, really big numbers to get fairly accurate estimates for this. Until eventually, somebody said there's got to be a better way. Because they were doing all of this without a calculator too. They did not have Desmos to show them a nice graph and not even have to calculate anything and type in f of 2.5. The reason that we go over this, because these estimates aren't that good, right? A range of 6.1875 to 12.1875, it's really not that great of an estimate, and so we don't really use this to actually do any calculus these days. But the understanding of it is important, because as we go through, we're going to see how we can take this and get the exact area. Just to point you in that direction a little bit. 12 rectangles was better than 6 rectangles, right? So 20 rectangles would be even better, right? 100 would be even better. What would be the best if we could do it? How many rectangles? Would 1,000 be better? What about 1,000,000? Infinity rectangles. So that should, in your mind, make your calculus mind be thinking just a little bit about the limit as the number of rectangles approaches infinity. So if we could do a Riemann sum where the number of rectangles approached infinity, then we could get the exact amount. So that's kind of what we're working towards. Now, tonight, you're going to be doing Riemann sums with left and right endpoints, and you will just get these kind of terrible estimates. Typically, textbooks and problems on the AP exam, they ask you to do it with a pretty small number of rectangles, usually not ever over 10, because otherwise it just takes you forever to do the problem, and you still don't get that good of an estimate. So it's really about understanding how to do them and not so much that the estimate is good right now. So you'll have to do some of these, but we're going somewhere with it, is the reason that we do these. So your assignment that you will have that will be due tomorrow is page 299, and you're going to do 25, 27, 29, 31, 32, 33, and 35. And for these, you are welcome to use your calculator or Desmos for these, so that you do not have to calculate all of those by hand. Let me just make